All right, so today we will have nuclear scientist Antoine Bourget, who will tell us about quiver decay and fission. Take it away.
Thank you very much. Thank you for joining this Quiver meeting. It's always good to speak at the Quiver meeting. And yes, indeed, I didn't notice, but of course, I'm in the Atomic Energy Commissariat, and I will talk about decay and fission, so it's appropriate. Okay, I will dive right in the topic. This is based on joint work with Marcus Sperling, who will talk in the second part. So stay tuned. If you get bored by my presentation, in half an hour you will have his side of the story, and Zheng Hao, who is in the audience. These two papers here. And okay, the point is about a story that we've been working on also with Julius, Amihai, and many other people about these Hasse diagrams for Higgs branches of supersymmetric theories. And okay, I will first summarize briefly this story that maybe most of you know already, so I will be quick and focus on the new things. So the story is as follows. If you take a QFT or an SCFT with 8 supercharges, for instance, in 4 dimensions, then there is a geometric incarnation of the Higgs mechanism, which is the nested singularity of the Higgs branch. And I refer to this paper, from which I've lazily copied several pictures for the beginning here. So for instance, just to remind you, if you take SQCD, so for instance here SU3 with 6 fundamentals, well, this is a theory which has a Higgs branch, which has 10 quaternionic dimensions, and it is stratified as follows. So there is at the origin, when the hypermultiplets have 0 VEV, then the gauge group is not broken. So this is where you have the SU3 theory, and that's only at a point. And then you can break the gauge group, but you can also partially break it to SU2 along a 5 quaternionic dimensional locus, and then completely break it. So there is this stratification of the Higgs branch, whether the gauge group is completely broken, partially broken, or not broken at all. And so this is the Higgs mechanism. The Higgs mechanism, you have degrees of freedom that become massless or massive, depending on how you see it. And this corresponds hitting these singularities. Okay, so these pictures are not very easy to draw. So instead, we draw Hasse diagrams. So this Hasse diagram is the way that we encode the previous picture. Each dot here represents a locus on the Higgs branch. Here you have a 0-dimensional locus, 5-dimensional, and 10-dimensional. And when you move from the smallest dimensional point to the top, you Higgs the theory more and more. You see the transverse slices. So if I go back to the previous drawing, the transverse slice, which is what is pictured in blue here, this is a transverse slice. So this is the Higgs branch of the theory after you've partially Higgsed. Okay, so this is the depiction. And now how do you compute efficiently this? Well, we have developed over the years a long program with magnetic quivers. So provided you know a magnetic quiver for the theory, which means a quiver, like the one drawn here, for which the 3D n = 4 Coulomb branch is equal to the Higgs branch of the theory that you want to study. If you find such a quiver, then you can apply a quiver subtraction algorithm, and this allows you to derive the Hasse diagram. So how does this work? Well, probably you've seen talks about this if you've been following the Quiver meeting. You start from the initial quiver, and then you identify certain patterns in the quiver that you can subtract, and you proceed like this iteratively. So from here, for instance, you would identify that there is a fine Dynkin D4 diagram in here that you can subtract, arrive here, etc. So this is a story that we have developed over the past few years. And why did it take so long? Well, the idea is simple. As I said, you subtract, say, either a fine Dynkin diagrams or A-type quivers, and then you have to rebalance. I won't go into the details, it's not too important here. These two steps seem to be very easy, but then there are difficulties. The first one is, actually, I said subtract a finding A type or other things. There can be many, many things. Each type of Higgsing corresponds to subtracting a particular diagram. And that's my first comment here. We need to know what are the possible things to subtract. And again, over the years, we have been able to compile a list of possible things to subtract. And so, for instance, this picture here, which is from, again, copied from this paper from 3 years ago, is a partial list of the things that you might have to subtract. So you can recognize here the affine A-type diagram, the affine E-type diagrams over here, D-type, also non-simply laced, F4, G2, but then also some more exotic things over here. In this particular 3 here are found in the as slices in the affine Grassmannians of certain groups, and then you have some more exotic things over there. And this list is not exhaustive. We know that there are other things, and that's a limitation, of course, on the algorithm, because this is really an input which is needed. Then the second thing, which is not really a shortcoming, it's more a feature of the Quiver subtraction algorithm. It's a very rich point, but which is only partially understood, is that sometimes it's not enough to subtract and rebalance. You need to add a little something to the quivers, which we called decorations. So let me again give you an example. This is not the main point of the talk, so I don't want to give all the details here. But basically, if you start from a simple quiver, such as this one here, if you apply naively the algorithm, you subtract, you see that there is an affine A2 diagram here that you can subtract a first time, and then a second time. But then once you've done this, if you ignore these red decorations there, then you obtain this quiver, which would tell you that the point that you've reached is a free theory. But actually, it's not the case. You have something more. And this additional slice here can be seen only if you've kept track of these decorations. And the exact meaning, the exact definitions of these decorations is not entirely clear. We have been studying those kind of quivers in those papers here, but we have a clear brain picture, and we have a clear understanding of what are the effective rules to compute with those, the phase diagrams. But for instance, it is still not known how to compute the associated Hilbert series for the quiver here in the middle. So, okay, this is a work in progress, and I won't bring an answer here. But it's just to mention that this is one thing that you have to deal with if you apply quiver subtraction. And the third comment is that the quivers that you produce with this algorithm are not the magnetic quivers for the Higgs theories. And this, I already mentioned it at the beginning when I was, sorry, I will go back to the, beginning here. The quivers that you get are the quivers for the transverse slices, as shown by these brackets. You start from the SU3 theory, and then the Higgs theory is the SU2, which is the transverse slice between this locus and this locus. In the first slide, this was the blue line here. But you see, you never get the magnetic quiver for this blue line, which would be a fine D4 quiver. You never get this by doing quiver subtraction. So,
but I mean, it's the thing you subtract, right?
Yeah, exactly. The thing you subtract would be the elementary transverse slice. Yeah.
You could ask, what can you subtract? And then it's going to be the magnetic quiver of the theory.
So here, of course, this is the only thing there is, because it's just, there are just 3 nodes. But in principle, if you have a much larger diagram, then if you want the quiver for the Higgs theories, you don't get it immediately, at least with this procedure.
Sure.
Yes, of course, it's
in principle, you could do it. It's just super annoying, I guess.
Yes. Yeah.
Good.
So, okay, so these are just comments. Again, I don't want to say that these are negative feature of the algorithm. It's just That's what physics tells us. This is, if you do quiver subtraction in this way, you have these features. You need to know the slices to subtract, unless there is some insight that we don't have at the moment. And you need to include these decorations. And yeah, you just don't get immediately the magnetic quivers for the Higgs theories. And so in this talk, I will mention this new algorithm.
Antoine, can I add something on the
Yes.
last slide?
Yes.
So on point 1 there, you gave these nice tables of some possibilities. So I wanted to ask, can you say what the analogous classification problem is in, I don't know, hyperkähler cones or something, which is equivalent to the problem of enumerating the quivers that you can subtract? And also in that problem, is it clear that everything, sort of every, I don't know what the solution to that, but every transverse slice or something has a representation as a quiver, which you could then subtract?
Yes, these are very good questions. So for the first part, what is the, I guess your question is, what is the mathematical formulation that this is an answer to? Mathematical question. So these are, I would say, the isolated thing. You know, you want things that you subtract, so there would be transverse slices. So you want isolated singularities. That's the point. Isolated, conical, symplectic singularities, probably. Even though you might want even more, because maybe you want to subtract sometimes non-normal transverse slices. So depending on your definition, this might not be called symplectic singularities, but okay. So yeah, the key point is isolated singularities. And then whether all isolated singularities admit a quiver representation like this, probably not. Well, definitely not with the restricted definition that we have here. Probably the simplest examples would be the E-type Klein singularities. They don't have a quiver description like this. Even the D-type, well, the D-type the D-type you have using the twisted diagrams, which are, no, sorry. D-types, okay, you can write with an orthosymplectic quiver, for instance, SU2, but okay, it's already a bit different from that. So yes, probably not. There is no reason why this unitary quiver that I'm using here should cover everything. But that's part of the game, is to extend the definition as much as possible, to come up with new objects whose Coulomb range describe as much as possible. And yeah, that's part of the game.
There's a new class by Namikawa.
Right, there is, but his class can be I don't know what you refer to, but it can be considered as U1 quivers with different representations, right?
Yeah.
On the edges, yeah.
It's satisfied. I mean, it's a single slice in an arbitrary dimension.
Yes.
No intermediate slices.
Yes, sure. Yes, that's a good example of another. Okay, so that's an example for a thing which is not in this list, but it is an isolated singularity which admits a quiver. And
Paul points out that there is a generalization. It is a generalization of their class.
Yes, I see the chat. Namikawa's class is a generation of, yeah, exactly. It's a generalization of this part here. Yeah. So yes, of course, there is much more. Okay, I pointed out this list, which is from, as I said, 4 years ago, and now there have been recent progress. So this is very exciting. Okay, so in this talk, I want to present a new algorithm, which has different features. In particular, it doesn't have these 3 features here. It has other aspects, so I will show this. Okay, so it's also based on magnetic quiver. It's just a different algorithm. The crucial point is that we will not need to have an a priori list like the one that I showed just a minute ago. We don't need this anymore. So this is a very good feature of this algorithm. The second is it produces the quivers for the Higgs theories. So it's really going in the direction of Higgsing. And the third point is we will not need decorations here. You might wonder, oh, how come we don't need decorations anymore? Because they seem to be there. Of course, the reason is we will go in another direction to get the, so if you want in the diagrams here, we won't go from the top to the bottom, but from the bottom to the top, and there we don't need decorations. But let me show an example and then it will be clear. An additional bonus that we get in this algorithm is that it's extremely simple in the sense that the quiver that you start with has a given shape, and this shape will never change. It will just, the quiver will just become smaller, so that's what we call decay. It's like a molecule, and then the components become smaller, or it can fission, as we will see, but the shape never changes. And this means that a computer implementation is extremely straightforward. And actually, I think Marcus will show that we have indeed implemented it in Mathematica. And another byproduct of this algorithm is that it allows to discover new elementary Higgsings. So that's the physical terminology, or as Craig asked, new isolated symplectic singularities. Okay, so, and I want to insist that it complements the quiver subtraction algorithm. And I will mention why at the end. But it's really, these are really two algorithms which work together. And okay. So now let me first show you on an example, and you will understand how it works. It's extremely easy. So I take on purpose a very trivial example here. This is a quiver which, you know, if you write it in a framed way, it's a very elementary quiver, but it will illustrate my points. And then Marcus will show much more interesting, physically interesting examples. So okay, let's consider this quiver here, 1, 1, 2, with 3 links, 2 links, and 1 link. And the algorithm works as follows. First, you list all the quivers which are smaller. What do I mean by smaller? I mean you reduce some of the ranks, and you find that there are exactly 5 quivers which are smaller than this. Oh, sorry, I forgot to say the good quivers, which are smaller. This is important. In the next slide, I corrected it. So they need to be good. So the balance of all the nodes need to be greater or equal to 0. And there are little subtleties that I will mention later. But okay, so you enumerate all the good quivers, which are smaller than the initial one. Here you find that there are 5. Then the second step is you find all possible ways to combine those smaller quivers in a way that when you add them up, you are still lower than the top one. So let's see what it gives in this particular case, where you can take this one alone, or this one alone, this one alone, this one alone, or this one alone. So these are 5 possibilities. And you see that you can also combine these 2 here. If you add these 2, you get exactly that. So this is fine. So there are actually 6 sets of quivers which are smaller than the top one. And now these 6 quivers, they are naturally ordered in the same way. We say that the quiver is there.
Can't you add the 0, 0, 0 guy to any of them?
So no, you cannot add the 0, 0. Good point. I was about to mention this. Of course, adding 0, 0, you would get infinitely many. So you remove 0, 0. And so actually you should consider all the non-zero ones and add them in all possible ways. Then you find that there are, and then if you do this, then you should consider that the empty set is the one which with no quivers at all. Again, I have a slide later where it's very precisely written. So all in all, we have 6 sets, and then they are naturally ordered. I mean, the intuitive order. So this is the smallest, this is the largest, and then, well, there is the natural order. Again, if you want the formal definition, it's given on the next slide. But here I want to give the intuitive version. You just write the partial order, and the claim is that's it. That's the Hasse diagram for the Coulomb branch of that starting point quiver. And importantly, you see that here we have 2 quivers, while in all the other points we have only 1. And this is what we call fission. So you see, you can really think of a kind of a nuclear reaction where you start from this. It can either decay, 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 or it can fission into 2, and here one of the 2 can decay, and etc. So that's it. So you see that we have obtained the diagram already. We don't know yet the geometry of the transverse slices, but then this geometry is computed in a quite straightforward way. If you have a decay, it means that one quiver becomes smaller. To compute the geometry of the transverse slice, you just do the subtraction. So you compute the difference between the two, rebalance, and that's how you get the transverse slice. So it's very straightforward. And when it's fission, up to some technicalities that I will also mention later, basically, if the two resulting quivers have the same GCD, if you take the GCD of all the ranks, it's an A1, and if it's not, it will be another singularity, which is called M. But okay, I just want to say that this is easy to compute. And the point I want to emphasize is it's quite different from the quiver subtraction, where we first needed to know the geometry of the transverse slice, then we subtract and we get the diagram. Here, we have it the other way. We first get the diagram and then compute individually all the transitions. Okay, so that's the resulting thing. You could, of course, check that this is the correct result by applying quiver subtraction, and you would get exactly the same thing. But here you just have this feature that you have this decay or fission. So let me phrase it in a precise way now, and it will you will see that Philip's point is addressed. So and I write this like explicitly just to show how simple it is and how simple it is to implement, in particular in the computer. So a quiver will just be a matrix, the adjacency matrix of the graph, and K is the collection of the ranks. And then you consider this set. This is the set of the good non-zero quivers, which are smaller than the initial one. So it's the set of rank vectors. And you see, you only need to care about the rank vectors because A is fixed once and for all. All the quivers have the same shape. So you take all the K primes, which are smaller than K, non-zero, and K prime should be good. And so good is mostly this inequality. I add this condition here that is good just to exclude, for instance, instanton moduli space, which are technically not good. But okay, this is again a detail. So you construct this set. These are the good lower quivers. And then the leaves are just the unions of all the sets of good quivers. So L0 is the empty set, and then LM is, so this notation means multi-set. You can have repetition of the same quiver. So I have to pick a symbol for that. And basically, the only condition is that all the Ks are in V0 and their sum is smaller than the initial K. So this is how we get the set of all leaves. And then the partial order, again, I won't try to explain what this means, but it basically is the translation of the intuitive partial order that you have on the quivers. Basically, since each leaf is a set, it contains a number of elements, and this number of elements can either grow if you have fission, or stays the same, or decrease if you have a decay to nothing. And okay, this explains exactly how it's computed. Again, I don't want to insist too much on these technical details. It's just to show that it is perfectly rigorous and prone to implementation.
So there's a comment from Saclay in the chat who asks to explain why this is a sensible thing to do.
Yes, good point. So I think Marcus will say a word. So I will mention at the end how this comes from. Let me first show that this kind of cartoon, that the graph of the quiver, this adjacency matrix, never changes. So this is what is pictured by this, the side of these dots. This is kind of the atomic illustration, and it can fission or decay. And as I said, the geometry of the transverse slices is given in the case of decay by difference of the two quivers that decay into each other, or fission is A1 or M. And also another technical point, for those who know what it is, that there can be a multiplicity. Sometimes a transverse slice can be a union of several cones. It's just given by how many quivers can decay. So for instance, here you have two quivers. They are identical. They can both decay to this. We don't know which one it is. So then we just put two arrows, by which we mean the transverse slice is a union of two cones. So I'm almost done.
So a quick question here.
Yeah.
So the question whether on top you have just one leaf in the whole symplectic singularity, or whether this is actually two leaves, like for example in the nilpotent cone of O, there's a splitting into two leaves, which are really two leaves, if it's even. So would you say that if you start with one quiver, it's actually always one leaf, or could it be two leaves as well? Like, do you have any way to check that?
I would say if we start with okay, this applies only to unitary quivers. I would say if you have if you have one quiver, then you have one leaf on top.
Okay.
Yeah, I would say this. I mean, the claim is it's really this. So yeah, there is only one empty set on top.
Okay, makes sense. Thank you.
Yeah. So maybe here, okay, is a good point to say in 1 minute. Again, I don't know what Marcus will say about this, but to answer Sakura's question, where does this come from? Well, I would say we had a physical approach to this. Like we made experiments, many experiments, and we tried to infer the general laws. And at some point, we found a very simple law, which is this, which seemed to agree with every experiment we could make. So we claim as physicists that this is the rule that quiver subtraction seems to follow. It can be proven that this is equivalent to the standard subtraction when you have 3D mirror symmetry, for instance. So that's one confirmation. Also for certain setups in which there is mathematical certainty on what is a diagram, like a fine Grassmannian or stuff like this, we can also check that this gives the same. And in general, we don't have a proof. And actually, this is one of the things that I think could appeal to mathematicians, that since the formulation is very simple, there might be a way to like go ahead, take the Braverman, Finkelberg, Nakajima construction of Coulomb branch and prove that this gives the stratification. I don't have such a proof, and this would be, yeah, someone else should do that. But yeah, the claim is based on many, many examples, and Marcus will show them. And finally, I think I have 1 minute, maybe a bit more, to tell you about this bonus, this byproduct, which is we can use this algorithm to scan through all quivers and just find those which cannot fission or decay to anything apart from nothing. If we find such a thing, then if our algorithm is correct, then it means that that thing corresponds to an isolated symplectic singularity, or physically an elementary Higgsing. So the way it works, it's some kind of convex linear algebra thing. So for instance, if we do it for the 2-node quiver, the most general 2-node quiver, you can parameterize by a matrix, which is like this. So I assume that there is no loop on the nodes here. So I put -2 on the diagonal, and then some integers a and b, and by symmetry I can assume that a is here and ab is here. I take standard non-simply laced edges, so one of the entries is a multiple of the other one, and I put arbitrary ranks here. So this is the most general 2-node quiver, and then you can easily check that you have solutions, which mean quivers which are good and which have nothing that they can decay or fission to if a square b is larger than 4. And then you have some optimization like this. So you have you can make a plot where K1 and K2 are on the axis here. Each point represents a quiver. And then basically, if you are in these cones, then you can decay or fission to lower ones. So you have to find the lowest non-zero one, which are these red dots here. This one and this one, corresponding to the 2 possible solutions to this equation, a greater than 2 and b greater than 1, or a is 1 and b greater than 4. And we find the 2 possible classes of isolated singularities, which can be written as quivers, with 2 nodes. And we find the a Klein singularity and the yb singularity, which was found recently in the mathematical literature by Paul, who is in the audience, and collaborators. And okay, so this, I just showed this 2 node, which is kind of trivial just because I can draw pictures, but then you can do more general cases. And we did the exercise for 3 nodes, and we find this table, which we claim is the complete list of 3-node quivers, which are isolated singularities, whose Coulomb branch are isolated singularities. So this is the complete list. And you see that we recover a lot of things that we have found more or less recently, we or other people have found, in particular this YL, some classical things, the A-type, some nilpotent orbits. We find the G2, the D3, the A4. We find these J slices that we found in a paper with Julius last year. And then there is an additional one, the one in red here, that we couldn't find in the literature. So yeah, that's one example of the applications of this new algorithm, that you can find such outliers. So now there is kind of a challenge. Can we characterize mathematically what this is? And can we identify a physical situation in which this quiver would appear?
Antoine,
Yes.
the A4, it's just a special case of choices of orientable planes. So it's not, so there is a whole class of AN even.
Yes.
They will be just, consequence of the work we did, Jan.
Yes. I agree. This is a twisted Fine-Linkin diagram. So yes, that's
right.
This is not a surprise.
Right.
Just
right.
Of course we had to find it. So again, this is just the output of a completely automatic algorithm, and so of course we find many expected solutions.
I see. Okay. Thank you.
So there is no surprise with A4. So the surprise is really on this. Well, I don't know if it's a surprise, but the only thing that we could not identify in the literature is this red one. So, and presumably there is now a very natural question is, well, can you do the same computation for an arbitrary number of nodes and then have the full classification of isolated singularities that can be written as Coulomb branches of good unitary quivers? Paul asks what dimension it is. Well, it's always the sum of the ranks minus 1. So it's 4 quaternionic, so 8 complex dimensions.
It's just A4. 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 There's nothing new, nothing fancy.
No, but I think he asks
the
about
new one. Sorry.
Yeah. So it's also 8-dimensional as A4, same dimension as A4, but something different. In the paper, we give so it has isometry SP2, so USP4, I think. And yeah, we give the Hilbert series in the paper, but yeah, we don't know much about this guy. Okay, and now I think my time is out. So I think we should continue immediately to Marcus and take questions and everything at the end.
Let's see if there are some questions now. I see that.
Or if there are questions specifically for me.
Let's have some questions. But first of all, let's just briefly thank Antoine, I would say, because this was very nice. And yes, let's have.
Yes, it was very nice. I have a very quick sort of technical question. So you mentioned that part of the algorithm is that you write down quivers with lower ranks, but the same shape.
Yes.
So what happens, for example, if you have, say, an adjoint loop on a single node? If you reduce the degree of that node to 0, does that count as changing the shape?
No, of course, zeros are allowed, as you see here.
Yes.
So zeros you can just ignore. So for instance, this quiver with a 0 here, it's just, this is just the standard A1 quiver. And it would work exactly the same with loops. No
okay, so this is sort of formal. I mean, in principle, this is a quiver with a different shape, but sort of formally, you can decorate it with 0 rank nodes such that it has the same shape.
Yeah. So when I say same shape is, sometimes it can be smaller. Like if you can have nodes with rank 0. But yeah, again, this example shows there is not more exotic than what is shown here.
All right, thank you.
Okay, good. Any more questions for Antoine now? Or are we ready for Marcus? Okay, I think we're ready for Marcus. Let's thank Antoine. Just one more time, and I'll also start a new recording.